think we're okay with kind of understanding the equilibrium potential for different ions. Let's review that a little bit. So if we have the membrane potential on the y-axis, and I have told you that the sodium equilibrium potential is plus 40 sodium, and I've also told you that the equilibrium potential for potassium is minus 90. And whatever ion we think about in that universe, and if I move the membrane potential anywhere along, well, anywhere, ions are going to move in a way that the membrane potential becomes equal to the equilibrium potential. So if we have only sodium, things are going to move until the membrane potential becomes minus 40. If we have only potassium, then things are going to move in a manner that the membrane potential becomes minus 90. What if we have both of these ions? What happens then? It's kind of like a tug of war, right? Because sodium's wanting to move things to plus 40, potassium is trying to move things to minus 90. Who wins? Well, if they both were equally permeable, so if they were equally permeable, there should be kind of like an average between the two, right? It should be like plus 40 minus 90 divided by 2. The average of 2 should be somewhere in the middle, right? That's not the case. They're not equally permeable. Potassium is way more permeable than sodium because this potassium has more leak channels. So it has more channels, so it's more permeable. So it allows the movement of potassium much more than sodium. Which means what? Which means this average that we just did, there'd be like a little bit different. So it would be multiplied with how permeable they are. It's more permeable here, less permeable here. So when we're averaging it, we need to take that into account. It turns out instead of being in the middle, somewhere closer to potassium equilibrium potential. Does that make sense? So if we do that weighted average, if you really like to think about it that way, the membrane potential is sitting somewhere closer to the equilibrium potential of sodium. I'm sorry, potassium, not that, because there's more leak channels for potassium. This particular membrane potential, which generally sets, I'm going to call it resting membrane potential. Okay. Now, in a normal cell, it's not just potassium and sodium. We have other ions as well. We have calcium. We have chloride. All these other things. What about them? Right? What about them? Well, two things we need to ask. What is their equilibrium potential? And what's their permeability? Because it looks like that's what the resting membrane potential depends on, isn't it? So the resting membrane potential depends on the equilibrium potential of all the ions, right? And it depends on the permeability of the ions. I'm going to come back to this point because we're going to talk a little bit more details about this. But those are two things that depend on. So if I talk about calcium, calcium has an equilibrium potential just like very positive, just like around here, like very, very far up actually. But that's not going to influence much because the permeability of calcium is pretty low. And what about chloride? Chloride actually has equilibrium potential that's actually very close to the resting membrane potential that we already have. So the current resting membrane potential that we have is minus 70 millivolts. The the chloride is minus 65, so it's pretty close. Yeah, that's why it's like, it is taken into account, but doesn't affect that much. But anyway, so taking all of the ions and their permeability into account, this is the resting membrane potential, it's minus 70. That's not true for all cells though. Some cells have it a little bit different. Most neurons, resting potential is minus 70.